Hi, today I'm going to be going through AS Physical Chemistry. I'm doing the AQA specification, and today I'm going to be doing bonding, and I'm going to start with 3.1, which is the nature of ionic bonding. So we know that ionic bonding is the bond between metals and non-metals, and in this bond, metals lose electrons to become cations, and non-metals gain electrons to become anions, and we can see this in bonds such as NaCl, and here is the electron subshells. So we have Na, which is 1s2, 2s2, 2p6, and 3s1. Then when it becomes Na+, it loses an electron, so it becomes 1s2, 2s2, 2p6. And then we see this for chlorine, but the other way around, so it gains an electron, so instead of being 3p5, it becomes 3p6. And the goal of ionic bonding is to achieve full outer shells. So we can see this with group 1, typically becomes 1+ ions, because that completes their outer shell, and it follows. So group 2 is 2+, and then on the other side, group 7 is 1-, and group 6 is 2-. This is because they want to be full outer shell, so this either means tending towards 0, because that would mean the previous outer shell is full, or tending to 8, because that means the current outer shell is full. But transition elements are a little different because they have partially filled d subshells, and so can form different ions with multiple different charges. We can see this in elements like iron, which can be like Fe2+ or Fe3+. And you can see the subshell electron arrangement. And this is because when transition elements undergo ionization, 4s electrons are lost before the 3d electrons. But the similar energies of the 4s and 3d subshells allow for successive ionizations in many transition elements, which results in different ions with multiple different charges. Okay, so here's 5 compound ions, and you need to know their molecular formula and their charge. These are the only ones you need to remember, and they're important for a lot of equations. They appear often. And so we have the nitrite ion, the carbonate ion, the sulfate ion, the hydroxide ion, and the ammonium ion. Okay, and so the next thing we need to talk about is determining the formulae of ionic compounds. And so this is because the positive and negative charges in total must cancel out. So for example, you have magnesium, which is 2+, because it's a group 2 metal, so it forms a 2+ ion, and it bonds with Cl, but we know that Cl is a group 7 element, which means it's a 1- ion. So we need 2 chloride ions to bond with 1 magnesium ion to form MgCl2, which is an ionic compound because the total charge is neutral. So what ionic bonding is an electrostatic force of attraction between oppositely charged ions. So this is 1 positive ion, 1 cation, and 1 negative ion, an anion, and these bonds are very strong. So now we need to talk about the structure of ionic compounds, and so these form giant lattice structures where positive and negative ions pack together. And so here's my drawing, although not very pretty, but a representation of every ion is electrostatically attracted to ions of the opposite charge in all directions. So I know I've just done a square, but you have to imagine that from one positive ion, every other direction is negative, and vice versa. So for one negative ion, every direction, every bond it has is a positive. And these bonds are very strong, like I said before, and so it takes significant energy to overcome these electrostatic forces. Okay, and the last thing to talk about is the properties that they have because of this structure. And so the first one is a high melting and boiling point, because the lattice must be broken apart. Every bond in the lattice must be broken apart. And as I said before, these electrostatic forces are very strong, and so it takes a lot of energy to overcome this. The second is that they can conduct electricity when molten or in solution. This is because the ions can now move freely, and that means they can carry charge. And this leads on to the third property, which is when they are solids, they don't conduct electricity. And this is because the ions are firmly locked in place, which means they're unable to move and therefore can't carry charge. And the last one is they dissolve in water. And water is a polar molecule, which means it attracts the charged ions in the lattice via ion-dipole forces, and that pulls them apart from the lattice, dissolving it in the water. Okay, and that's the end of 3.1. Thank you for watching. Bye!